Sure.
Welcome to the project presentation on memory and cache hierarchy optimization for graph analytics, presented by the group CacheMe, consisting of the members Siddharth, Abhijit, and Aditya, as part of the computer architecture course. In this project, we come up with different cache optimizations to improve the IPC of traces of various given graph algorithms. So first we'll look at a short introduction of caches. Caches divide the storage hardware into multiple levels and they are designed for speed over storage and they serve as a latency hiding intermediary to the DRAM. The highest levels have very low latency but also very low capacity and each successive level has increasing latency and capacity. Caches rely on the assumption that data is spatially and temporally correlated. Caches load data from the slower memory into the faster memory to decrease lookup time, but there is only so much space available to the cache. So where do we look to improve the IPC by optimizing caches? We want to minimize the cache misses at all levels. One obvious way would be to make the caches bigger. Also, there are multiple ways to divide the data in the cache. We could have an inclusive cache or an exclusive cache or neither based on the distribution of data between the levels of the cache. Another important aspect of the cache is its replacement policy, which is how we determine which line is going to be replaced when a new line comes in. Next, we are going to look at some inclusion policies. First, we have the inclusive policy, which states that each level of the cache is a subset of each of its lower level. When a new data comes in, it is stored in each level of the cache. And when a data is removed from a certain level, it is also removed from each of its higher levels. Next, we have the exclusive cache, which is like an opposite to the inclusive cache. Here, each line is present in exactly one level. When we have new data, it bypasses the lower levels of cache and goes to the highest level. And when we remove a line from a certain level, it is moved to the next lower level of the cache. And finally, we have the non-inclusive cache, which is like an intermediate of both inclusive and exclusive. Here, we don't have any restrictions on how many levels a line could be present in. Also, there are no restrictions for how we evict them from the cache levels.
Next, let us look at the cache replacement policies which we have implemented. So basically, we have implemented the self-explanatory replacement policies that are LRU, LFU, MRU, and MFU. So as the name suggests, LRU stands for the least recently used block will be removed when it is marked as a victim. And apart from this cache replacement policies, we have also tried out FIFO and some of the predefined uh, cache replacement policies which were present in the ChampSim code, such as SHIP and SRRIP. But unfortunately, it did not work for us. They were giving lower results than what we were getting for the other four cache replacement policies. So then we started tinkering with the replacement policies which we decided upon. So as seen from the graph, the replacement the LFU is working the best uh, on an average. The replacement policy is the best replacement policy is LFU, and as we can also observe from the miss rate that the miss rate for LFU is the lowest. Next, we tried to change the size of the L1 cache. As we can see from the graph of the IPC, that it does not change on increasing the size of the L1 cache. Also, the changes in miss rate are also insignificant. Next, we tinkered with the size of the L2 cache. It showed a gradual increase in both IPC and miss rate for uh, for all of the both the replacement policy. However, the IPC was better in LFU and also the miss rate was smaller in LFU. For the LLC, we got a significant result. that on increasing the cache size, the overall IPC increases and the misrate decreases. For comparison in between the two replacement policies which we are using, LFU shows better result in comparison to MRU. So, from the last slide, we concluded that it might be possible that if we increase the size of the LLC, then IPC will go on increasing. But we actually wanted to practically check it once, so we tried to increase the cache size at every level as high as possible. But at a certain point, it got saturated, and then it was not actually gradually decreasing but slowly, that like for the third or fourth decimal places it was showing minor decrease.
After running over several permutations and combinations, we narrowed it down to the following conclusion regarding the replacement, inclusion, and hierarchy for the graph programs. So here are the best obtainable IPC values for each trace, and the highest IPC is obtained in a non-inclusive policy using LFU as a cache replacement policy, and the cache size of LLC being around 262 kilobytes for the SSSP3 trace. During our testing, the highest IPC configuration we saw earlier worked best for almost all traces. Considering cache replacement policies, LFU outperformed the rest in all but one trace, where instead MRU outperformed the rest. Cache hierarchy Hereby, cache hierarchy does not always follow the same trend. The order is sensitive to a number of simulations and cache sizes, although it can be observed that increasing the cache size of LLC by 4 times worked the best.